Hi. Today I want to continue our study of Laplace equation and the round. So today the topic is fundamental solution. Of the Laplace equation. Last time I found the general form of radial solution. So radial solution is function u of x, which depends on the model x distance from the origin, and such that delta u of x is 0 for x different from 0. And this function had the following form. U of x had the form a logarithm module x plus b if n equal 2. And a module x to the power 2 minus n plus b if n more or equal than 3. So we have these functions, and no wonder that we have this condition, because when x goes to 0, ux goes to infinity. And there is no way to discuss what is Laplacian at 0. It makes no sense. But we can say much more about this function. So to this end I wanted to introduce multi-dimension modifier. So let me remind you what we have, what is one-dimensional modifier. It is a function phi of x on the line phi in C infinity 0. So this 0 means that the function is 0 outside some finite segment. Yes, not only it has everywhere all derivatives, but it is 0 outside some finite segment. So phi of x is 0 for module x more than 1. Phi of minus x equals phi of x. Phi of x more or equal than 0. And the integral, say from minus 1 to 1, phi of x dx equals 1. Now, instead of minus 1 and 1, I can write from minus infinity to plus infinity, because the function anyway is 0 for module x more than 1. So we have this function. And now consider other function in an n-dimensional case. We consider the function, say, psi of x equals phi of module x divided by integral over all Rn phi x module x So what is this function? Psi of x, because it is phi of module x, is 0 for x module x more than 1. One thing. Other thing, almost obvious, that let me write here, psi of x is also in C infinity 0 at the space Rn. So it has all the partial derivatives of all orders. Psi of x equals 0 for module x more or equal than 1. Next, it is psi of x is more or equal than 0. Instead of this oddity, it is anyway, it is a function of module x. So, of course, it is odd, more or less it is spherically symmetric. This function depends only on distance from 0, so it is a radial function. Psi of x is a radial function. And the integral over Rn psi of f dx equals 1. Why it is 1? No, because, let me write, integral phi of module x divided by integral phi of module x dx. So it is a constant. So equals 1 over integral phi of module x dx times integral phi of module x dx, which is 1. Yeah. So this is a good modifier in n-dimensional space, and we will use it. And now it is a function, so if in one dimension the picture of this function is something like this, yeah, is minus 1, 1. Then, in 2 dimensions, let me draw the level lines. So this, the level 0 level lines, it is 0 outside, c equals 0. And here, c is not 0. It is like, its relief looks like this. Or if you look from the side, you will see something like this in the xy plane. Yeah, I'm sorry. This axis go through. This is the picture. It is z equals psi of x1, x2. Yes, so it is the graph of this function. No, we can call it a head function, but let's just call it modifier, or simply yes. And now let me make a small jump. Let us call it, we write phi of x instead of psi of x. So psi was a temporary notation because I cannot here write in the left and right hand side the same function, but now after we define the function phi, we define psi of x. We denote this function by again phi of x. So phi of x is a modifier, notation for modifier function, which has all these properties in any dimension. Now, in each dimension it is a different function because function of different number of variables, but nonetheless, in general, we have this good notation. And now, to make it a real modifier, we have to introduce a parameter. So we write phi epsilon of x equals 1 over epsilon to the power n phi of x divided by epsilon. It is all in Rn. Yes? So we take, for n equal 1, we had this, it is initial function phi, and for epsilon less than 1, we have this function. Yes? This is the graph of this function. Now here we have simply a similar thing, so instead of this surface, we have this surface. Yeah? Why epsilon to the power n? Because it's the rule of change of variables. If you say instead of x, write x divided by epsilon, this means that you make transformation in the x, x1, x2, xn, just shrink everything like multiply all x's by epsilon. So if initially the function was concentrated in a ball of radius 1, then after this transformation, this function is concentrated in a ball of radius epsilon. Yes? And after such shrinking, the integral of the function, if you shrink like this, will be multiplied by epsilon to the power n. Yes? If you remember what is, how it is done, no, I would say the Jacobian of this transformation is equal to epsilon to the power n. And to keep this condition that integral phi epsilon of x dx equals 1, we have to divide by the same epsilon to the power n. So we have this function phi epsilon of x. And the use of this function is the following. We use this function, say, to approximate any continuous function by smooth function. So, in one dimension. If, say, fx is just continuous function in one dimension, then we write f epsilon of x equals integral, say, f of y phi epsilon of x minus y dy. Yes? And this is the result. We take this function, which can be continuous, but maybe not more than continuous, it has no further regularity. And then you, at the point x, it is, say, the y-axis, we multiply it by this modifier, it is phi epsilon of x minus y. Yes? So we take the function phi epsilon, it was first around the point 0, and then you moved it, so the center is at the point x, and then you multiply and you integrate the product. Yes? And the result will be a function f epsilon of x if you do it for all epsilon. And then we proved that this function first is continuous, first is smooth. Yes? So f epsilon is smooth. I mean smooth, C infinity has all the necessary, all derivatives. So if you need some number of derivatives after this operation, you always will have them. And we have that f epsilon goes to of x goes to f of x when epsilon goes to 0. So this smooth function f epsilon becomes closer and closer to the function f as epsilon goes to 0. We can do literally the same in n-dimensional case of Rn. Yes, and define f epsilon of x equals integral f of y phi epsilon x minus y dy. Here integral over Rn. But we integrate with respect to y, and this function is 0 outside the ball around the point x of radius epsilon. So here we have this point x. The function phi epsilon is 0 outside this ball of radius epsilon. Yes, so it is ball at the with center x and radius epsilon. So outside this ball the function is 0. So we can write integral over this ball, or we can over any larger domain, in particular over all the space Rn. And f epsilon goes to f, tends to f, when epsilon goes to 0. Moreover, we can substitute here function fx in this integral such that the function f is merely integrable. Yes? So the function can be discontinuous and even be unbounded. If this integral exists, if integral module fx dx is finite, so the function is integrable, then f epsilon of x equals integral f of y phi epsilon of x minus y dy is defined. And smooth. Smooth means C infinity. Yes? And if the function is, say, piecewise continuous, that at every piece where this function is continuous, it is this function phi epsilon will be closer and closer to function f when epsilon goes to 0. And if you have some discontinuities or some more severe singularities, there this function behaves somehow. And we are interested now in the following function. We had the function u One moment. U of x, which is in fact u of module x, equals a logarithm x plus b if n is 2, ax to the power 2 minus n plus b if n more or equal than 3. So both this and this function are unbounded. They are go to infinity when x goes to 0. So, but beyond this, these functions are good. You see, smooth functions, and moreover, they are harmonic functions. So, outside of 0, it is a harmonic function. Its Laplacian is 0. So this means that, and beside this, the function logarithm x in the logarithm module x, and here module x, logarithm module x, logarithm module x, dx over R2 is, no, not over the whole R2. We are interested in bounded domain. Module x less than some r, or equal. Yes, so we take in the, say, plane some circle of radius r. Yes? And in this circle, this function is integrable. So this integral less than infinity. No, simply because it is integral is equal to integral from 0 to r, 2 pi r module logarithm module r. Logarithm r dr. I do it in polar coordinates, and this function not only is integrable, it goes to 0 when r goes to 0. So this is continuous function which is goes to 0 as r goes to 0. This means that this integral is finite. And we can define this function. One moment. For this function, ax to the power 2 minus n, integral for module x less than r, module x to the power 2 minus n dx. Let us go to the spherical coordinates, so we integrate over a sphere of some radius r, and then we integrate over all these spheres, yes, this way. So it is equal integral from 0 to r, and r to the power 2 minus n, it is this. Now we have to write the area of the sphere. It is times some constant which times r to the power n minus 1. So the area of the sphere in n-dimensional space of radius r is proportional to radius to the power n minus 1. No, for example, in the plane n equal 2, so the length of the circle is proportional to radius. In the three-dimensional space n equals 3, so the area of the sphere of radius r is proportional to r squared, and so on. Yes, dr equals integral from 0 to r, r to the power 1 dr. Anyway, this is less than infinity. So this is also good. And so this means that we can define the function u epsilon of x equals integral u of y phi epsilon of x minus y dy. Whew. So this is our function. U is this function. It is a radial function which is continuous outside of 0. Now let me make it more special. This constant b is not interesting for us. Let us set a temporally equal 1. Yeah. So u of x is either logarithm x or modulo x to the power 2 minus n. In fact, we have to add some other coefficient for our needs, but currently let me keep it this way. So we know that both this function in two-dimensional space and this in any n-dimensional space are harmonic outside of 0. Now the first observation, u epsilon of x is a function in C infinity. It is a general rule. Why? Because we can differentiate it with respect to x. Yes, this does not depend on x. So we have to write, say, du epsilon dx equals integral u of y. How to differentiate? X is parameter. To differentiate a function with respect to parameter, we have to differentiate this integrand, the function which is integrated, with respect to the same parameter, and then integrate it. dxi, for example, this does not depend on x, so only this. D phi epsilon at the point x minus y with respect to d xi. Yes? So we'd have to differentiate, let me write this, d phi epsilon dx minus y at the point x minus y dx. Now, the function phi epsilon is a smooth function with compact, it's called compact support, the way the function is maybe not zero, so outside support it is 0. Some function with compact support. And so this integral converges, this continuous function, and so on. And we can further write d2 u epsilon dxi dxj, and by the same rule it is integral u of y d2 phi epsilon dxi dxj at the point x minus y it is dy. And again, this is a smooth function, so this shows that this derivative exists, and so on and so on. So we see that all derivatives exist. So it is a smooth function. First thing. Second thing is the following. Second is the following. Laplacian u epsilon of x equals 0 for module x more than epsilon. Yeah? Here you see Laplacian of u is 0 for module x different from 0. And here it should be a little farther, at least at the distance epsilon from the origin. So here we have a ball of radius epsilon, and outside this ball the function u epsilon is harmonic function. So how can you know this? Let us do the following. Let me write the function u epsilon in equivalent form. U epsilon of x equals integral u of x minus y phi epsilon of y dy. Now, why this is the same? This is equal to integral u of y phi epsilon of x minus y dy. It is one form of this integral, it is other form. Now how to go from this to this? Let me denote x minus y equal z. Y equals x minus z. And so after this, I'm sorry, d y equals minus dz. And so this is equal integral x minus y, it is phi of z, phi epsilon of y, it is x minus z, minus dz, which is the same as here. Simply instead of y, here it is written z. Yes? Yes. So this means that we can use this form. Now, what does it mean? So consider one function. No, let me find let me write this function. So again, u epsilon of x equals integral u of x minus y phi epsilon of y dy. And here in this integral, x is parameter and y is the variable of integration. So how to find d2 u epsilon dxi. First, du epsilon dxi equals, we have to differentiate this with respect to x. So this depends on x, this does not depend on x. It is integral du dxi at the point x minus y, phi epsilon of y dy. d2 u epsilon dxi square equals integral, again differentiate with respect to x, we have to differentiate only with this, d2 u dxi square at the point x minus y, phi epsilon of y dy. And delta u epsilon equals sum d2 u epsilon dxi square equals, no, have to sum sum d2 u dxi at the point x minus y phi epsilon of y dy. Okay, now if you want to find Laplacian of function u epsilon at this point x, yes, we have to here consider integral of consider the function the Laplacian Laplacian this function u at this point which are not x but x minus y. This is x, this is say x minus y. Yes. And then we multiplied by this function phi epsilon and integrate over the whole y. But the function phi epsilon is 0 outside the ball of radius epsilon. Yes? This means that this function phi epsilon of y is 0 outside the ball of radius epsilon, around the point x. So if x is farther from origin than epsilon, the distance is more than epsilon, then this ball does not contain the origin. Yes? And we know that Laplacian of u, so it is integral Laplacian u at the point x minus y phi epsilon of y dy. Yes, Laplacian of u is 0 everywhere outside the origin. So this means that here everywhere Laplacian is 0 inside this ball. So it is 0 if module x more than or equal, no, more than epsilon. In fact, maybe equal, no, okay, more than epsilon. So what we have that the function which we constructed, u epsilon, is harmonic function everywhere outside this ball of radius epsilon. And then in this ball it is maybe harmonic, maybe not. It requires further study. Next property is the following, that u epsilon of x is in fact u epsilon of module x. Yeah? So this is also a radial function. No, it is simply because the function u of x is a radial function, and phi epsilon is a radial function. So if you say turn the point x, it is going to the point, say, x1, which is at the same distance. It's the same as we turn all the space so that the point x goes to the point x1, and then all our construction also turns. So if you turn the function phi epsilon like this, then it will be the same as we take the same phi and epsilon just moved here. And so this means that after rotation, by arbitrary rotation around this point 0, this function transforms into itself. Yes, so it is a radial function. It does not depend on the direction from origin to the point x. It depends only on the distance. And now I am approaching the crucial statement that in fact u epsilon of x is the same as u of x, coincide with u of x for x more than epsilon, more or equal in fact. Yeah, so it's this way we somehow recovered the function u. If u epsilon is, no, I would say, if you are in the plane, then the function u of x is logarithm of the distance to the origin. It is more or less, it's graph along some array. And u epsilon is like this. This is epsilon, and u epsilon is something like this. So it is the function which is here somehow smoothed. So here, after this smoothing, the function does not change here, and here it's infinitely high. This summit becomes just a smooth hill. Not very high, and the same for dimension 3 and more. So this is serious, a little more serious, and let me remind you the statement of the Gauss divergence theory. Gauss divergence theorem. The Gauss divergence theorem says that the following. So if you have a domain, bounded domain, in the space of any dimension, domain D, and the surface S of this domain. At every point of S, we have external unit normal n. Moreover, we can integrate the functions inside this domain, this volume integral, and we can integrate the function on the surface, which is the surface integral. Yes? And then suppose you have a vector field, say vector field B of x, vector field in D. And then the Gauss theorem is the following identity: integral over D, divergence field B dx equals integral over the surface S B dot n ds. Now, in particular, we have integral yes, so this is no simple result of integration by parts. Yes. Now suppose that divergence B equals 0 in D. Then the left-hand side is 0, and the right-hand side should be 0, integral over S B dot n ds is 0. Now, the last statement can be visualized as follows. Suppose we have a flow of incompressible fluid, like water, in the space. Yes, and suppose that incompressible means that this is divergence of this velocity field is 0. Then the amount of and suppose we have domain D in this space. Then the amount of the fluid which enters this domain, yes, so this is this vector field. Here is enters, here it exits. Yeah? So the amount of fluid which enters domain equals to amount of fluid which exits domain per unit time. Yeah? As much fluid as enters it, the same amount exits. Now, similarly, we can consider more interesting domains, such that the boundary consists of several components. For example, we have our domain with a hole. Yes, so it is domain D. It is the S1. It is S2. So our domain, its boundary has two components. Then we should draw what is external normal, unit normal. So here it looks this way, and here it should look this way. Yes, because it looks outside of domain. In this case, it is inside this hole. And but relative to this hole, if you want to keep this normal really external, so if you have this closed surface in this space, normal should look outside. It is so we have to draw normal here. Then the integral changes sign, and so this is n. Yes, so it is looks like more natural choice of the direction of unit external normal. And in this case we have the following. So if divergence B is 0, then you have integral over S1 B dot n ds minus integral over S2 B dot n ds equals 0. Yeah? So, no, for example, here we have a source of liquid. The liquid is flowing in all directions, like this. Yes? And if the flow of this fluid is, incompressible, so its divergence of velocity field is 0, then the amount of fluid which flows through this surface S2 is equal to amount of fluid through surface S1, because the difference is 0. Yeah? And now let us consider in particular the following. Consider the function u of x such that Laplacian u equals 0, identity equals 0, in S, in D. Yes? Then we know that Laplacian u equals divergence of gradient of u. So gradient of u is vector u1 du dx1 du dx2. So gradient u equals du dx1 du dx2 du dxn. And the divergence gradient u, we have to differentiate this with respect to x1 d2 u dx1 plus d2u dx2 plus and so on, plus d2u dxn, which is nothing but Laplacian u. Yes? And if Laplacian u is 0, this means that divergence of gradient u is 0. Now, let us, this function u in our consideration is exactly that radial function. U of x equals u of module x equals logarithm module x if n equal 2, module x 2 minus n more equal than 3. So we know that this function is harmonic beyond 0, and let us consider the following domain D. R1 less than module x less than R2. So our domain D is domain between two spheres. Yes? D. so it is R1, so it is S1, it is S2. And our yes, if this Laplacian u is 0, it means that integral over S1 gradient u dot n ds equals integral over S2 gradient u dot n ds. Yes, it is easy to verify this because what is gradient u? If n equals to gradient u equals first it's vector directed along the radius, and second this length of this vector is 1 over x. So it is x divided by modulo x square. Yes, 1 over x. And now so it is this vector. Integral over S1 gradient u dot n ds equals, it is nothing but a circle of radius r1, so integral from 0 to 2 pi r1 gradient u, it is x divided by modulo x squared times 1 over r1, r1 divided by r1 square, d theta equals 2 pi. So we see that the integral or the flux through this circle S1 does not depend on its radius. It is always equal to 2 pi. Yes. Moreover, we can draw any other curve which encircles 0, and the flux through this curve, say it is some surface S3. S3 it is arbitrary closed curve containing origin inside. Because of the same Gauss Theorem, the flux through any such circle or say any such surface in two-dimensional space is equal to the flux through this circle with center at origin. And so it is equal to 2 pi. So let me state it. For any, let me write curve S containing zero inside integral over S gradient u dot n ds equals 2 pi. Essentially that it does not depend on this circle. It is because the divergence of this vector field is 0. Again, it is interpreted in the terms of flowing fluid, that if you have a source of fluid at the origin, then the flux of the fluid through any closed curve is equal to the productivity of this source. We have the amount of the fluid which exits from inside this curve equals to amount of the fluid which enters through this source. Now, similarly, if you are in n-dimensional space, then in n-dimensional space, n more than 3, then gradient u equals, we have to take its derivative in the radial direction. It is equals 2 minus n x divided by module x, so it is n minus 1. N minus 1. And now, if you take the sphere of radius r, with center, it is S. Integral through S, gradient u dot n ds equals 2 minus n r divided by r to the power n minus 1 one moment. Sorry. It is a function decrease like model x to power 1 minus n. Yes. Times area of the, let me write, area of S, which is equal 2 minus n. Area of S is proportional to r to the power n minus 1. Rn times some constant t, r n minus 1, which is equals 2 minus n times c. Again, it does not depend on the radius. Yes, and again we can imagine a source of incompressible fluid which is issuing from the origin, and the amount of fluid which flows through any sphere on the, in general, any surface which contains 0 inside is the same. We get as much fluid as much it was entered through the origin. Okay. So we almost forgot what we did it for. So u epsilon of x equals integral u of x minus y phi epsilon of y dy. We have this function, and gradient u epsilon of x equals integral gradient u at the point x minus y phi epsilon of y dy. This is gradient of u epsilon. And now let us consider this factor. Suppose that we are far from the origin, farther than epsilon. Then, this is the point y. So, first we had the vector field gradient u of x minus y. So we had a vector field gradient u like this. Gradient u at the point x. Yes? So it is issued from the origin. And now we shifted this field, and it starts to start at the point y instead of the origin and instead of the point 0. Yeah? So what happened with its flux through the sphere of no sufficiently large radius, S? So I consider integral through S gradient u at the point x minus y dot n of x ds x. Yeah. No, note that it corresponds to point to x, and y is just parameter. It is the flux of the field. We can do the following. Instead of moving the source of the field, yes, the point where was the center, from where the fluid was moving, we can shift the sphere in the opposite direction by y, equals integral over s minus y. Yeah, s minus y, we take every point of s and moved it in the direction of y, but in the opposite direction. So s minus y is this sphere. So it is s, and this is s minus y. Integral over s minus y, this initial field, gradient u of x dot n of x ds ds at the point x. Yeah? So you got it, that we shifted, first we shifted the field, it is this field u of gradient u of x minus y, and integrated it along a sphere. And now instead of this, we did not shift the field, we shifted the sphere in opposite direction. And now we can use the Gauss Theorem. If this shift was small enough so that this y is less than the distance over which we shifted, y is less than the, we shifted by y, so y is less than the radius, so radius of the sphere is large enough. Then we have two surfaces which encircle one and the same singular point where the fluid is originating, and the flux should be the same. So they are equal. Yes? They are equal because here I shifted the sphere and for the same vector field, and this is equal to integral over S, the initial grad u of x dot n of x dsx. Yeah? So why did I tell all this? Consider the function u, this field, gradient u, u epsilon. We consider integral over S gradient u epsilon of x dot n of x dx. What is gradient u epsilon? It is integral over S, gradient integral gradient u of x minus y phi epsilon of y dy ds. Yes? So I substitute here gradient u epsilon. So here we have integral over the sphere, and here we have integral, in fact, y is changing inside a small ball of radius epsilon, yes, because the function phi epsilon is 0 outside this ball. And now we can change the order of integration. It is integral phi epsilon of y times integral over S gradient u of x minus y dot n, I'm sorry, ds and dy. And this is the integral over the sphere of shifted gradient u of x minus y. We shifted by y, gradient u. And we remain in the domain where the Laplacian is 0. This means that this is equal to integral phi epsilon of y times integral gradient u of x n of x ds dy. Yeah? So here we can, instead of x minus y, write u of x, because this is the shifted vector field, and this is the initial vector field, and they are equal, these fluxes. Now, because this is constant, it does not depend on y, so it is integral phi epsilon of y dy times integral gradient u of x dot here dot n of x ds. And this is 1. Yes? And so the result is the following. What we started from, it is integral over s, yes, gradient u epsilon and dx. After all this transformation, we have equals to integral gradient u dot n ds. Yes, so the flux for the smoothed field and for the initial field are equal. Whew. So what does it mean? The function u epsilon is radial. U epsilon of x equals u epsilon of module x. We have one thing. Second thing, Laplacian u epsilon equals 0 for module x more than epsilon. Third thing, integral over s gradient u epsilon dot n ds equals integral over s gradient u dot n ds for any sphere s of radius more than epsilon. And fourth, we know that u epsilon of module x equals let me write it for n equal 2. This my reasoning do not depend on the dimension a logarithm module x plus b. We don't know what is a and b, but if this is the flux is the same, then I have found the flux. The flux is 2 pi a. This means that flux integral over s equals 2 pi a. A is this one. And what does it mean? This means that a here is 1, because for u is equals 2 pi a equals 2 pi. A equals 1, because this is equal to this. A equal 1. This means that u epsilon of x equals logarithm module x plus some constant b. It remains to make sure that b is 0. B is 0. So you know that u of x equals logarithm module x without any b. And so u epsilon of x equals integral u of y phi epsilon of x minus y dy. Yes? And now the point is the following. The function u of y logarithm x looks like this as a function. So here it grows, but very slowly. This means that the derivative of function of gradient of the function u of y module gradient u of x equals 1 over module x. Yeah? So this means that function here changes very slowly. And we multiplied by this function phi epsilon, which is concentrated around the point x in the ball of radius epsilon. This means that u of y minus u of x less than epsilon divided by module x. Yes, because if the function u of y, its derivative is less than 1 over x, 2 epsilon. Then in the ball of radius epsilon, it cannot change much. It changes not more than, even less than 2 epsilon divided by module x. Yes? This means that u of x minus u epsilon of x less than c divided by module x. No, c epsilon. Okay, 2 epsilon divided by module x. On one hand. On the other hand, if u epsilon equals logarithm module x plus b, then u epsilon of x minus u of x equals b. Yeah? If b is not 0, then what happens? U epsilon of x minus u of x does not go to 0 as module x goes to infinity. You see, because this difference really goes to 0 as x goes to infinity. So, on one hand, the difference should be b, constant. On the other hand, the difference goes to infinity. It can happen only if b equals 0. Hence, b equals 0. Okay, so we found that important thing that let me write the result. U epsilon of x equal u of x for module x more than epsilon. So our function behaves like this. No, in two-dimensional case it is x. Yeah, so this is graph of this function. Now imagine that it is a surface. For u of x it goes to minus infinity, and for u epsilon of x it looks like this. It is epsilon. Yeah? So this it is smoothed only in the epsilon ball around 0, epsilon neighborhood. That's it. So we found the basic properties of the this smooth function u. No, it requires some labor for, and next time, which will come very soon, we will consider further. I have to continue to explain what is the fundamental solution. Yes, so I will do it next time. For now, let us finish. Have a good time. Bye.